One of the most popular AI chatbots is ChatGPT, but have you ever wondered what the G, what the P, and what the T stand for? It's Generative Pre-trained Transformer. And you actually need to know what those three words mean if you want to assess the strengths and the limitations of AI chatbots. So today, let's learn what GPT really means. So when breaking down GPT, I do think it's important to go from understanding what generative means to what pre-trained means, and then finally what the transformer is, because all three really matter. And as it turns out, when you're training a large language model, there's really three different levels of training that occurs. At the very base level, you have something called pre-training. This is something that we usually think of and associate with training a large language model, but there are two other steps that are actually really important as well. There's a step called fine-tuning, where we can actually change the parameters of a model and have the model become a little bit more specialized. And then also there's this thing called reinforcement learning through human feedback that is also representative of another really important step of how chatbots work the way that they do today. So we're going to go through all three of these things to really understand what do these things mean. So let's start off with generative. And in order to understand generative, I think it's best to understand what chatbots do and how they actually kind of act like autocomplete machines. In fact, they really do act like autocomplete machines, except they work in a recursive manner. Okay, so what does that mean? I started you off with a sentence here, right? There's a fragment of a sentence. The dog ran across. And if you took all of these four words together in their order and the context in which you're finding them, you could probably predict what the next word is going to be. The, right? But I think what's really interesting with the generative part of GPT is the machine then takes this statement, the dog ran across the, and this becomes the new input. This is where the recursiveness comes from. And so when we're trying to figure out, well, what is the next word? How do we keep the sentence going? And this is actually a very simple statistical problem. If you have enough data and have enough examples of how text goes together and how some words are associated with each other, you can actually come up with a list of words that might be likely. Maybe the dog ran across the street. Maybe the dog ran across the lawn. Maybe the dog ran across the grass. These things are really probable because we've seen similar sentences have this kind of a structure in a training data set. And I think what's really interesting here is you could start to see how some words like lawn and grass start to encapsulate the same meaning or at least similar meanings. And so we have a whole bunch of words that we could choose from to put in next. Some of them are going to be very likely, like street, lawn, or grass. Some words are going to be not likely. For example, the dog ran across the sun is probably not so likely, and the dog ran across the broom also not likely. And so what you can see is we have these candidates of words to choose. We choose one and we continue this problem. In this case, we chose the most common answer that we saw here, the one that we expect, the dog ran across the street. And I think what's really interesting to understand about the generative part of this is it doesn't always choose the most likely answer. You might think that here the most likely answer is to, right? The dog ran across the street to do something. There is a chance every single time you interact with a chatbot that it's going to choose maybe the second most likely answer or the third most likely answer or the fourth most likely answer. And so just to give you an example here, we're not going to select the most common word to, but we're going to choose rather, and we can continue to fill out this sentence until we have a situation in which maybe we could just end the sentence. The dog ran across the street rather than walking. Maybe that ends the sentence, but that is basically a sentence, and that's how you get meaning. We're just taking words, we're figuring out what the next word should be, we're feeding that back into the system, and basically building out a sentence from there. That's all that the generative part means when it comes to generative pre-trained transformer. And so the next thing that we're going to do is we're going to look at pre-trained, because training these models is actually pretty expensive. If you actually look at one of the most advanced Google models, one of the Gemini Ultra models, it's not publicly available how much data they were trained on, how much text and video and audio was fed into the system. But what is publicly available is it costs Google $191 million. So huge data sets are being inputted as training material for these models. But what does it actually mean to train a large language model? How do you take text from all across the internet and Wikipedia and Reddit and books and all of this information and actually have a large language model learn something about the association between those words? Well, that's where we're going to get into the pre-trained definition. And so we're going to focus on training on text. You can obviously do this on videos and pictures and audio as well, but text is a very easy way to start. But let's just start off with the sentence that we ended up with, right? The dog ran across the street rather than walking. It's a pretty simple sentence. It's one that you might find on the internet somewhere. And what you would do is feed the sentence and many sentences like it to the computer and have it delete one of the words. Here we have the blank ran across the street rather than walking. And we know that we deleted the word dog, and training basically means that we're going to try to get the computer to learn based off all these examples of other text that it has access to. What should we plug in into this space? Now, we know the true answer is dog. That's what we started off with. But maybe there's some statistical relationship between the word cat and all of the words that we have in the sentence, right? The cat ran across the street rather than walking. That changes the meaning of the sentence, but that's a pretty plausible word that we could put into that slot. Same thing with a goose. A goose could run across the street rather than walking. Same thing with a moose. So what you can see is we're building meaning into the function of this word. And so we can start to build this list of likely candidate words and build meaning into the sentence. Now, I will also say there are many nonsensical words that might be here as well. So for example, we can't really say that the fridge ran across the street rather than walking. Even though there's that famous joke, right? Is your fridge running? We know that that is a thing that exists. So maybe you might put fridge in here if you're trying to be funny or you're trying to be silly, but that is just statistically less likely than a dog or a cat or a goose or a moose. Okay, if we can do that for one word, all we really have to do is extend that to a different word. Maybe this time we say the dog blank across the street rather than walking. And we know that the word is ran, but what other words statistically could fit in here? And I think what's really interesting is when you start seeing words used in different ways, words that have different contextual meanings. So for example, we could say, man, the dog flew across the street rather than walking. And in that sense, if I say that sentence to you, you're not literally thinking about a dog flapping its wings or flapping its ears and floating through the air. I'm using the term flew figuratively to mean that that dog was moving fast, right? Fast like the wind. So in this case, flew could have the same meaning as the word ran, and they would be really, really similar functionally in this spot. Now, obviously, we could also choose likely words that slightly change the meaning of the sentence. So, for example, the dog barked across the street rather than walking. Maybe it was too lazy and just wanted to get the attention of whatever was on the other side of the street. Or maybe there's some contextual information a couple sentences before this, or just somewhere associated with this sentence to know that maybe it rained a lot. And so maybe it might be likely to say that the dog swam across the street rather than walking. So you start to build all of these words together into a statistical understanding of functionally what are they doing inside of a sentence. And again, the tricky and very interesting thing here is some words can look exactly the same to the computer, but have completely different meaning based on our understanding on our context. For example, if we say that the dog flew across the street, meaning that it was flying, levitating, floating through the air, we know that that is not a likely meaning or function that fits in this space, even though it's the same word that we used earlier. So how does the computer learn this context and learn this meaning? This is a process called embedding. And all embedding is taking a word, finding statistical associations with that word, and then kind of placing that word into a theoretical space. Whereas you get words that mean the same thing being in the same space and words that mean the different thing in opposite spaces. This is a lot easier to represent if I'm just going to use a simple axis, right? Just a singular axis to kind of spread out different ideas or different words. And so let's just start off with these two ideas. I'm showing you two images, one of a salamander, one of a crocodile. And what we can see is that there are some similarities there, but what we're really interested in, what is their differences? And so if you were to place these animals on this singular axis, you might place them kind of far away. You might place the salamander over here based off of its size, and you might place that crocodile over here because of its size, right? Because they are different in their size, and that gives us some differentiation of those words. We could take more animals that we find in the context of text and see that there's an elephant, but there's also the same thing as an elephant shrew. Again, very, very different in size, but an elephant shrew is more similar to size to a salamander than a crocodile, and an elephant is more similar in size to the crocodile than a salamander. So we can start to place these on this axis to kind of build understanding or meaning, right? And as you get more statistical examples of this, more examples of animals that you can place on this line, well, then you start building information. You can start to see, okay, everything on the left-hand side is going to be representative of a small animal. Everything on the right hand is representative of a large animal. This is a very, very simple embedding where we can say small animals on one side, large animals on the other, and in between we have some intermediates. Now, the use of this is when we're trying to figure out what word we should fill in into a sentence. For example, the blank fit in the palm of my hand. Well, you're probably not going to be searching for a large animal because large animals don't typically fit in the palm of your hand. If you just look at all the text that exists on the internet and in books, that sentence probably doesn't come up as often, whereas other sentences where we include the salamander, the shrew, the rat, these things are much more smaller, and so we can encode that information in a singular axis. The same way we might say, well, there's no way that a blank will fit in my room. Again, there's contextual understanding that we're probably going to be searching for solutions that are large in nature. A horse, a crocodile, an elephant, those would all be great candidates for what would fit in that blank. And so this is great. This is the purpose of embedding, again, to separate out words by their understanding, but also to group similar words together. And this is just using a singular axis. What we know about one of the models, GPT-3, is that it's not just a single axis that divides the information up. It's actually somewhere over 12,000 different axes that exist in this hyperdimensional space. And that's really hard to visualize, but just to show you how powerful it is to have multiple axes and having these ideas embedded in different spaces, I'm just going to draw another axis for you. Right here we have a vertical axis, it's perpendicular, and let's say that we want to encode or embed information about the animal's fluffiness versus its scaliness. So if we do that, if we build more information on top of that and try to encode scaliness versus fluffiness, then we get further separation out where, okay, maybe these two animals, right, the salamander and the turtle, they're pretty scaly, but they separate out based off of their size. Right? Maybe when we're looking at like a wolf versus a horse, I mean, they both maybe might be able to substitute for a large, fluffy-ish animal. And so in this top left-hand corner, we can see that, well, these two animals will probably be good candidates for filling in this blank. The sleeping blank cuddled her hand. Whereas at the other end of the spectrum, when you say the sunlight glinted off the giant scales of the blank, because of the computer's understanding of this word, it's probably going to select this crocodile more so than it would this wolf or even this elephant because of that information. And so this is basically what an embedding looks like. An embedding is just a multi-dimensional vector that puts these words or these ideas into different spaces. And one of the most important ideas that comes out of this is really that once you start embedding different words through their statistical usage in the English language, similar words are going to have similar embeddings, meaning that it becomes easier to find good candidate words to fill in the blank if we understand where to search for, which directions should we start searching. So this brings us to the last thing that we need to talk about, which is the transformer. Right? And the transformer is nothing but a data structure. It was actually developed by Google in 2017. It was one of the most important things that they used to build good translators, so to translate from French to English, for example. But the transformer, it's a way that a machine can get context of what the word means based off of what you find around it and where you find the word in a sentence. So for example, let's start off with a simple word, object. If I just gave you this word, object, and asked you for a definition to tell me what the meaning of the word object is, you might not know because there's different meanings of the word object. And so what you would probably ask for is like, oh, well, can you use it in a sentence? And so when you place this in the sentence, the object is placed on the table. Now we have some contextual information. And I've highlighted here the important part of this, right? What helps us understand what the word object means is the fact that after it, we have the words placed on. When you have that object placed on, that actually gives you a good idea of what the meaning of object is. In this case, a physical thing, right? An object is a physical thing on a table in this sentence. But again, this is not the only way that you can use the word object, because if I change the sentence slightly and say the object of the game is to win, this is no longer referring to a physical object. Now we're talking about a goal, a mission, or an objective. And again, how do we get that? A couple words after object, we have the word game, we have the word win, and that influences how we think about the word object. And it's no longer a physical thing in this case. In this case, it's much more abstract. One more example of the word object. If we use a sentence, the lawyer stood up to object. And I'm even pronouncing it differently because we pronounce this word differently when we use it as a verb. How do you know it's a verb? Well, first of all, it comes right after the word to. In this case, this is not a noun, and this is going to be a verb, right? So now we're talking about to object. Also, lawyers, the fact that you see the word lawyer, lawyers object all the time. It's one of the words we associate with lawyers all the time. So again, a slightly different meaning based off of the context of the words around it. When we're actually looking at context, this is what we call attention. And that's actually the name of the paper that Google wrote to introduce this data structure. It's Attention is All You Need. Very, very famous paper. But all attention is, in this case, is a way to figure out what other words in the sentence give meaning to the word you're trying to define. In this case, we're looking within the same sentence, so this is what we refer to as self-attention, but this just allows us to have context. All right, so how does this work with the embeddings, right? We know that words are embedded. So I'm giving you a very hypothetical example over here of how we might embed the word object. And so through textual information and statistical information, maybe the pre-trained version of this places the word object in this space of meaning. And without any other context, maybe this is where we start. But the important thing is this is only where we start. Because of the transformer, we can pay attention to other words. We can use meanings of other words to shift the computer's understanding of what this word is. So for example, if you use a sentence that is using the word object as a more abstract noun, well, we could shift from our original embedding to a completely different space that's a little bit more abstract. And now we have separation between the meanings of object on a table and the object of the game is to win. And you can kind of imagine for our third example, well, maybe from our pre-trained example, we can move in a completely different direction because we recognize through the transformer that this is probably going to be a verb. And when we push into a different space, we can encode or embed a different meaning. So the transformers are actually one of the key pieces of technology that allow chatbots and ChatGPT to build in nuance into a quote-unquote understanding of what you're talking about or how you're using the words. So that kind of explains all three parts of GPT, the Generative Pre-trained Transformer. But all of this really relates more to the pre-training phase. There's actually two other phases that we've built on top of modern chatbots to actually make the chatbots appear smarter, to appear to have more knowledge, to appear to be better in conversation. And those two things are fine-tuning and reinforcement learning. And it turns out these two things are actually very, very dependent on humans still. So we'll talk about these fairly quickly. So let's talk about fine-tuning. Fine-tuning is built on top of the pre-training. The way that I like to think about this is if pre-training is like the large language model learning language, fine-tuning is actually giving the chatbot different abilities. And so here's a problem. If you just took a pre-trained model and didn't do anything to it, and you gave it this prompt, question, help me generate a hypothesis. Because the pre-trained model can only act as an autocomplete, it's not actually going to answer your question. Instead, It's going to try to finish your sentence. It's going to give you that is testable and falsifiable. And again, these are statistical combinations of words that go together. There's some information and some meaning there, but that is not the behavior that we are interested in if this is a chatbot. What we would want to do is ask a question, help me generate a hypothesis, and maybe it answers us back, let me help you generate a hypothesis. That's kind of the behavior that you want. To do this, we build another level on top of the pre-training, and this is called fine-tuning. Specifically in this case, we can call this instruction tuning. What we need to do is feed the large language model a separate data set, actually modeling the behaviors and modeling the data that we would like the large language model to learn. So in this case, this is a new piece of data, right? A human had to write this to say, question, help me generate a hypothesis. Answer, sure. What kind of science are you interested in? This is a piece of data that can be built on top of the pre-trained model to teach this chatbot how to actually be a chatbot. In fact, this is how we get the chat in ChatGPT. If GPT is just there to be a really good auto-completion, this allows us to turn this into a chatbot. And the reason why this is so important, especially now, is a lot of the innovation and a lot of the usefulness of these chatbots are going to rely a lot on fine-tuning and reinforcement. Here's why. It's because we can start to feed thousands of examples of basic knowledge that any scientist would know or any biologist would know, right? Why are cells important? They are the basic units of life. You might want to think about these as like biology facts. And maybe the large language model was able to learn this just through gleaning information, again, off the internet and through Wikipedia and through all of the books that were fed to it. But if we want to make a specialized model specifically for science, you want to guarantee that this chatbot knows that this association of words and this type of behavior is really important. This is approaching knowledge. This is getting closer to the computer actually learning a fact. Again, it's not quite there. This is not quite knowledge. The computer still has no idea what this actually means. But this is as close as we can get to the large language model storing a fact for other users in the future. And as you can imagine, this is a very, very simple example. We could start to build some domain-specific information, right? So for example, we could feed in data such as what is mechanobiology? Well, this field involves how physical forces affect cell function. You can start to see how we can build really important nuance into these models and tune these models to not just be good at language, but maybe potentially be good at science. The other thing that we're going to be looking at, the sort of last level of human intervention that is going to be really important, is actually called reinforcement learning. So when we're talking about reinforcement learning with human feedback, or RLHF, what we're really talking about is a human's ability to have some control over the behavior of the large language model. Sometimes, just like a child, some of the behavior that comes out of it is going to be great, and some of it is going to be wildly inappropriate. What you can do using reinforcement is really reward good responses, whatever good means to you, and then also sort of dissuade the model or completely prevent a model from providing feedback that is not good or inappropriate or harmful. And so here's just a really, really interesting hypothetical, right? Maybe the task is to answer this question. What are some good exercises for a beginner? This is a prompt that is fed to the large language model, and you can actually have the large language model spit out 4 different prompts, right? Answer A, answer B, answer C, answer D. And as a human engineer, you can go in there and rank these. You could say, okay, A is not a great answer because it's too complex, right? B is not a great answer because there's really no information there. C is pretty good. That sounds pretty helpful. D is very harmful, right? This is not advice that anybody should follow. So you can start to build this ranking system where you can start to reward the model and make it more likely to give you answers that look like C and less like D. And so this is important for many reasons. One, this is one of the ways that we actually can build guardrails into these large language models. As these things get more powerful, we want to make sure that they are not being used for dangerous activities or inappropriate activities. And so you can actually have humans in here working with the model, telling the model, yes, you can do this. No, you can't do this. In fact, what's really interesting about this is you can do this yourself. I took a screenshot of this because I wanted to show you at the very end of the prompt, you have a thumbs up and a thumbs down. you have the ability to do reinforcement learning with human feedback. And by clicking on some of these buttons, maybe you liked the feedback, maybe you didn't like the feedback, that can actually go in to help train the model for future uses. And one big word of warning, especially recently, there have been a couple of stories that have come out in the news regarding large language models and their ability to be really sycophantic. They make you feel like you're the smartest person in the room, the smartest person in the world. And even when you say, if you lead it with, hey, isn't this bad idea such a good idea? Isn't this bad idea the best idea that's ever that anyone has ever come up with? Because of the way that these models have been reinforced and the way that these models have been trained, they can sort of suck up to you. You don't want to be interacting with a chatbot that's not going to challenge your ideas. When we're talking about a good research partner is not always going to agree with you all the time. And as it turns out, if humans are training this, humans tend to like models that agree with them. Humans tend to like models that complement them. And so you just have to be really careful when you interact with these models today and in the future. So I want to leave you with 3 summary points that we covered today. The first one is that these chatbots really are acting like autocomplete machines. But as it turns out, acting like an autocomplete machine is actually not as easy as we think. You might just not pay too much attention to the difficulty of the problem of understanding context of a sentence and nuance in how words are being used, and is a word figurative versus literal versus a noun versus a verb. But these computers, through these giant vector spaces, are able to encode that and navigate through that space. That is a really tough problem, and one that the chatbots are solving every time you're interacting with it. The second thing is, I just really want to reemphasize how important the transformer is. We didn't really go through the mathematics of how the transformer works, but I do think it's important to note that this singular piece of technology, this data structure, is what allows these large language models to really have context in terms of the words that they're seeing and the words that they're spitting back out to you. The reason why sometimes we can be tricked to thinking that there's an intelligence there, that the computer actually knows what it's saying, is because it is so good at using the transformer to pay attention to the context of other words and how that influences where in the vector space it's pulling these words from. The last thing we want to end up with is this idea that humans are still really important. You don't just train a model and then you're done with it. Humans have to go in and do the fine tuning, and that's especially true if you want to make a model that's much more specialized for your domain. Like if you want to make a very specific physics large language model, or even like a scientific analysis and methods large language model, it really does take an expert, a human, to go in there to make sure that the model is tuned appropriately and fed correct information and accurate and appropriate information. The other thing too is reinforcement learning via human feedback that has humans involved directly. We have the ability to train these chatbots to answer in a certain way. We can thumbs up or thumbs down, all these different things. And the computers are still learning from how we're interacting with them. That's a very powerful thing. And again, that's something that we should be thinking about in terms of safety. And I think it's also just kind of important to recognize that these models can kind of lie to you. And it's not really the model's fault, right? This is the result of reinforcement, where sometimes humans can train these models to just suck up a little bit too much at the expense of fact, at the expense of truth, at the expense of knowledge. And it's not like these models want to lie to you. It's not like these models have a plan to lie to you. But because we're using reinforcement models and humans are in here saying that was a good response, that was a bad response, we are baking in human bias into these models, whether we like it or not. Our bias as humans is directly reflected in the chatbots and how they function. And because of that, because we all like to hear how great we are, we all like to hear how smart we are and how good we are and how awesome that idea was, chatbots are going to pick up on that and feel like they get rewarded for spitting that kind of information back to us. Okay, that's it for this video. Hopefully you learned a little bit about the basics of how these machine models work. We'll definitely get some practice on using these practically in the future videos, but I do think that it was important to kind of learn some background information without getting too much into the weeds. All right, till next time. See you later.